Good morning, everybody. Hope you are all healthy and safe. So, in today's lecture, we are going to begin with the new section 4.5, and in this section, we are going to deal with the function called as the Dirac delta function. Okay, so before introducing this Dirac delta function, we should know about another function which is called as a unit impulse function. So I'll just write it down for you guys what is the unit impulse function, because it is obtained, the Dirac delta function is obtained from, or it is obtained as a limiting condition of the unit impulse function. So unit impulse function is used in many physical models, like in many cases many mechanical systems are acted upon various force, external force, then only we get some output out of it. So the basic model of that force is given by this unit impulse function, which is denoted by delta A, which is equal to 0 when 0 less than equal to t less than t dot minus a. It is 1 by 2a when t lies between t dot minus a and t dot plus a, and it is again 0 when t is greater than equal to t dot plus a. So this is the unit impulse function, and we derive the Dirac delta function from this, or we don't derive it, it is actually the limiting condition of the unit impulse function. So as you can see, as the value of a decreases, the magnitude will increase, right? Because a is in the denominator, so the magnitude of delta a will increase. Also, if you take the integral from 0 to infinity of delta a t minus t dot, okay, this is delta a t minus t dot at the particular rate. So what do we get? I will split this into like from 0 to t dot minus a, and from t to t dot minus a to t dot plus a, then from t dot plus a to infinity. So the last two integrals will become 0. So the only remaining one will be from t dot minus a to t dot plus a, and delta a at that particular point is 1 by 2a into dt. So this is by integration, this is 1 by 2a into t, 2a is a constant, right? T dot minus a t dot plus a. So this is equal to t dot plus a minus t dot of minus of t dot minus a, so you will get 2a. So this value is 1. That's why the integral of this impulse function, this particular function from 0 to infinity, is obtained to be 1, and hence it is called as the unit impulse function. So this unit impulse function plays a quite important role in many physical models, and we will use the Dirac delta function to determine the Laplace transform and so on. So the Dirac delta function is actually, it is the limiting condition of the unit impulse function. As you can see, it is defined as limit a tends to 0 delta a t minus t dot. Okay, so it is the limiting condition of the unit impulse function. This was our unit impulse function. Now from this directly we can obtain these two properties. The second one is clear. Just now we have seen that it is integral 0 to infinity delta of t minus t dot will be 1, because integral 0 to infinity delta a of t minus t dot is 1, and limiting value will be the same, right? Limit and integration can be interchanged because they are continuous. So this property we have just now proved. Now in this case, that is delta of t minus t dot is equal to infinity when t is equal to t dot and 0 when t is not equal to t dot. So let's just write down what was delta a of t minus t dot. Delta a of t minus t dot was like 0 when 0 less than equal to t less than t minus t dot minus a. and when it was 1 by 2a when t lies between t dot minus a and t dot plus a, and it was again 0 when t was greater than equal to t dot plus a. So here t equal to t dot, that is only possible in this interval, right? When a is 0, right? So that is when a tends to 0, we get the value, limiting value of delta a 1 by 2a will be infinity. In these two cases there are no possibility of t attaining the value t dot, right? Because t is either 0 and it lies between, it takes all values which is less than, strictly less than t dot minus a. So we cannot get t dot here if we put a equal to 0 also. So in all other cases when t is not equal to t dot, these two cases will occur, and in that case we have delta a is 0. So limit a tends to a is 0, delta a is again 0. So the Dirac delta function is 0 when t is not equal to t dot, and it is infinity when t is equal to t dot by applying the limiting condition over here. So I hope these properties are clear for you. So this is about the Dirac delta function. So now, since we are discussing about the Laplace transform of many functions, we shall look into the Laplace transform of the Dirac function. So the Laplace transform of the Dirac function is given by L of delta t minus t dot is equal to e raised to minus st dot. Okay, so the Laplace transform of the Dirac delta function is e raised to minus st dot. So let's just move on to the proof of this, or how we can obtain what is the Laplace transform. We'll just look into it. So for that, let us consider delta of consider the unit impulse function, that is delta of t minus t dot. Okay, this is nothing but 0 when, I'm writing it again, that is 0 less than equal to t less than t dot minus a, and 1 by 2a when it lies between t dot minus a and t dot plus a, and again 0 when it is greater than, when t is greater than equal to t dot plus a. So I'm going to write this delta a in terms of the unit step function that we have discussed earlier. Okay, so how can we do that? So when 0 to t dot minus a, it is taking the value 0, and when t is greater than t dot minus a, it is taking 1 by 2a. So if I take 1 by 2a out common, it is like 1. So I can write this as 1 by 2a into the unit step function of t minus, instead of t minus a we have here t dot minus a. Okay, minus of the unit step function of t minus t dot plus a. So this is how you can express the unit impulse function in terms of the unit step function. So once we know or once we can express the this function in terms of unit step function, we know the Laplace transform of unit step function. So the determination of Laplace transform of the Dirac delta function will be easier. Okay, so let us determine what will be the Laplace transform of this unit impulse function, that is delta a of t minus t dot will be equal to 1 by 2a is common. The Laplace transform of the unit step function t minus t dot minus a minus unit step function t minus t dot plus a. You can just expand these two terms and see whether this is the same. It will be the same according to the definition of the unit step function. So what will this value be? So the Laplace transform of delta a of t minus t dot will be nothing but 1 by 2a. Now we know the Laplace transform of the unit step function t minus a is nothing but e raised to minus s into a sa divided by s, right? So here it will be u of t minus t dot minus a, so it will be e raised to minus s into t dot minus a by s minus e raised to minus s t dot plus a by s. This is the Laplace transform. So I'm just simplifying this, and e raised to minus s t dot is common, so I'm just taking that out common. And what do I get? I get e raised to sa minus e raised to minus sa by 2as, right? So we have obtained the Laplace transform of the unit impulse function. Now how can we determine the Laplace transform of the Dirac delta function? Now Laplace transform of delta of t minus t dot equal to Laplace transform limit a tends to 0 delta a unit step function, right? So this I can write it as limit a tends to 0 Laplace transform of delta a of t minus t dot. So this is equal to limit a tends to 0. What was the Laplace transform? E raised to minus st dot e raised to minus sa minus e raised to e raised to sa divided by 2sa. So e raised to st dot minus st dot is a constant, and limit a tends to 0 e raised to sa minus e raised to minus sa by 2sa. So according to our theorem, the Laplace transform was e raised to minus st dot. So this implies this whole term must be 1. So how can we find the limit? You can see that when I apply limit a tends to 0, the numerator becomes e raised to 0 minus e raised to 0, that is 1 minus 1, which is 0, and again this is also 0. So when I apply the limit, I get the 0 by 0 form. So you guys must be very familiar with it. So once we have 0 by 0 form or infinity by infinity form, we apply the L'Hopital's rule, right? So applying L'Hopital's rule, we get the Laplace transform of the Dirac delta function is nothing but e raised to minus st dot into limit a tends to 0, the derivative of the numerator, that is s into e raised to sa minus again s minus of s into e raised to divided by 2s, that is we are differentiating with respect to a, right? So s is getting cancelled, and what do we have? Limit a tends to 0, s gets cancelled on both the sides, so we get e raised to sa plus e raised to minus sa divided by 2. Now when I apply a tends to 0, it will get 1 plus 1, that is 2, so I get this whole term to be 1. So this is the Laplace transform of the Dirac delta function. Okay, so next we shall just do one example which depicts the same, and we shall solve an initial value problem. Okay, solve y double dash plus y is equal to 4 into the Dirac delta function t minus 2 pi, subject to the condition y of 0 is equal to 1 and y dash of 0 is 0. Okay, so when I apply Laplace transform, what do we get? Laplace transform of 4 into delta of t minus 2 pi. So this implies s square into y of s minus s into y of 0 plus s y dash of 0 plus y of s will be equal to 4 into, what is the Laplace transform of Dirac delta function? E raised to minus s t dot. Here t dot is 2 pi, right? So when I apply the values, y dash of 0 is 0, y of 0 is 1, so s square plus 1 into y of s minus s is equal to 4 into e raised to minus 2 pi s. Okay, so let's find the value of y of t. Y of s will be equal to s plus 4 into e raised to minus 2 pi s whole divided by s square plus 1. So in taking the inverse Laplace transform, of s plus 4 e raised to minus 2 pi s by s square plus 1. So this is nothing but, this is y of t, and this is Laplace transform inverse of bilinearity s by s square plus 1. What is the inverse Laplace transform of s by s square plus 1? E raised to minus 2 pi s by s square plus 1. Right. So this is nothing but cos t, and this will be 4 into this. Here we'll apply the inverse Laplace transform of unit step function, right? So sine of t minus a, here a is 2 pi, into the unit step function of t minus 2 pi. So this is our solution. So you can substitute the value of t minus 2 pi here and write it in a simpler form, like we get y of t can be written as cos t when it is lying between 0 to 2 pi, because in this interval unit step function is 0, and it is cos t plus 4 sine t minus 2 pi when t is greater than equal to 2 pi, because in that case unit step function is 1. And also, what is sine t minus 2 pi? That is nothing but sine t itself. So I can write this as plus 4 sine t. So this will be our solution. Okay, so this was something about the Dirac delta function, and if problems are given in terms of Dirac delta function, we can easily find the Laplace transform with the help of the formula that Laplace transform of the Dirac delta function is equal to e raised to minus s t dot. So that's it. We shall do more problems related to the same. So with this we shall wind up the section. So thank you all, stay safe and healthy.